Hey guys, today we're going to be talking about how to determine if a table represents a quadratic function. And to do this, we're going to go through a few steps, and some of this will be a little bit of a review from things we've done in the past. So we'll start with the first table that we have. It's shown right here. And whenever you have a table of values, the first thing you want to do is you want to check to see if it is linear. And to do this, like, we go up by 1 up here every time we go up with an input. So we're going to check the outputs down here, and we go plus 5. This is a 2, so plus 5, plus 5. We call this down here, we call this the first difference. So when you're checking to see if something is linear, you're checking the first difference. Everything goes up by 1, and since everything goes up by 5 down here, we would say this is linear. If the first difference is the same between every output here, we're going to be linear. Of course, that's because every input's going up by 1 as well. So you have the constant rate of change of 5 over 1, 5 over 1, 5 over 1. That's what makes this linear. So that's what we've done in the past. So let's look at a function that's not linear. And we'll see if we notice anything that's going on with this. So let's take this next function. We have 0, 1, 2, and 3. Then we have 8, 4, 2, 1, and 0.5, or 1/2. And if we look at this, well, everything up top, we're doing plus 1, plus 1, plus 1, plus 1. And on the bottom, if we look at that first difference, we go minus 4, minus 2, minus 1, minus 1/2. Now clearly we can see that we don't change by the same increment every time. We're not subtracting the same thing. So that tells us that this is not linear. Now we're going to want to go through some other steps here to figure out if something is a quadratic or not. So for this one, what we're going to look at, the first thing we should look at before we look at something called the second difference is there a pattern? There was no pattern of adding or subtracting here. Is there a pattern of multiplying by something? So to go from 8 to 4, what do you have to multiply by? Well, to get from 8 to 4, you'd have to take half. So you're multiplying by 1/2. To get from 4 to 2, you're multiplying by 1/2. So we have a pattern going, but it has to be consistent throughout everything. To go from 2 to 1, you'd be multiplying by 1/2. And to go from 1 to 1/2, you would multiply by 1/2. So there is a pattern of multiplying. And this should be somewhat of a review as well, because when you're multiplying by the same value, we call that an exponential function. So this is an exponential relationship here. And in fact, we're changing by 1/2. So this would be like a decay function. Everything is getting half and half and half as we go. So that's going to tell us what an exponential, or when we have an exponential function. Now let's look at our third example and see how things change for this one. Our third example, we have -3, -2, -1, 0, and 1. And on the bottom, we have -3, -7, -9, -9, -7. So inputs and outputs. All of our inputs increase by 1, and our outputs, let's find the first difference here. First difference, we go minus 4, minus 2, 0, and then plus 2. So that's our first difference. And if you look, the first difference is not constant. We're not changed by the same thing every time. So that tells us, since the first difference is not constant, it tells us that it's not going to be linear. If we look at the outputs, we can try and find a value that we're multiplying by to see if it's exponential. And you can kind of check really quickly. If you want to jump to right here, -9 times 1 would get you -9, but then -9 times 1 would not get you -7, so it's not exponential. You're not multiplying by the same value. So in order to check now to see if it's a quadratic, we're going to check what we call the second difference. So the second difference, you're going to take the first difference, and you're going to see how the first difference change from one to the other. So from -4 to 2, you go up 2. From -2 to 0, you go up 2. From 0 to 2, you go up 2. So this we refer to as the second difference. And if the second difference is constant, like it is here, you add 2, the first difference is changing by 2 every time. If the second difference is constant, that means we're of degree 2, which means we are a quadratic function. So this table here represents a quadratic function. And this is the new part for us. So first you check to see if it's linear with your first difference. If it's not, you want to check to see if it's an exponential. Is there a pattern you're multiplying by? If not, you can check the second difference, which right here is checking the difference of the first difference. And if there's a constant pattern there, then it's a quadratic. So let's go ahead and try a few of these on our own to see if we can tell if they are quadratics, exponentials, or linears. So our first one, we have 0, then 1, 2, 3, 4. If you want to try on your own, you can, and then check and see if you have the right answer. We have 5, 8, 17, 32, and 53. Alright, so we go up by 1 in all of our inputs. So let's check the first difference. First difference is +3, +9, +15, and then +21. That is our first difference here. So clearly the first difference is going to tell us that we are not a linear function. So then what we can check is, do we multiply by the same thing to go from each output to the next? So to go from 5 to 8, well, you would do 5 times 8/5 to get from 5 to 8. So that means we have to multiply everything by 8/5 for there to be a pattern and be exponential. So let's do 8 times 8/5, which is 64/5, which does not simplify, so it does not equal 17. So therefore there is no pattern to make it an exponential. So let's go ahead and check to see if it's a quadratic. So we go to the second difference here. So in our first difference, we go from 3 to 9, so that's +6. We go from 9 to 15, that's +6. We go from 15 to 21, that's +6. So since we have a constant pattern in the second difference, that means we are a quadratic function. So this table represents a quadratic. Alright, let's look at the other problems that we have here. Our next one, we go, let's do the orange one. We go -2, -1, 0, 1, and 2. And the bottom we go 11, 7, 3, -1, -5. So we go up by 1. In all of our inputs or outputs, we go -4, -4, -4, and -4. So our first difference is constant. And like we've seen plenty of times in the past, that means we are linear. We have a constant rate of change of -4 here. So the orange one was a linear relationship. And our last one that we'll do will be that red one. So the red one, we have -1, 0, 1, 2, and 3. And we go 3, 6, 12, 24, and 48. So if we check the first difference, we have +3, +6, +12, +24. So there's not a constant pattern. And if you wanted to check the second difference, you would see that it's +3, +6, +12. There's not a pattern going on there as well, like we're not constant. So let's see if we're multiplying by the same thing here. To go from 3 to 6, you'd have to multiply by 2. To go from 6 to 12, you'd have to multiply by 2. To go from 12 to 24, you'd have to multiply by 2. And to go from 24 to 48, you'd be multiplying by 2. Since we're multiplying by 2 every time, this is going to be an exponential function, a relationship going on here, multiplying by the same value. Alright, so that's all we have for today. A big part of mathematics is trying to recognize patterns because then it tells you certain relationships that exist. So go ahead and try some of these on your own. Determine if a table is linear, exponential, or quadratic. Alright guys, have a nice day.